Here is our first example of a projectile motion problem. Go ahead and read that through. I'm going to draw a rough sketch. So we have our supply plane needing to drop a package of food. The plane is flying 100 meters above the glacier at a speed. I'm assuming the plane's flying horizontally, parallel to the ground. We want to know how far short of the target it should drop the package. So the little dot I drew here represents the package. The package was in the plane, so its initial velocity is going to be that of the plane. But because of gravity, it will go and fall towards the ground. And it's going to fall over here, which means in order to have it land where we want to, we need to drop it earlier than the target. Again, we're ignoring air resistance, which of course in a situation like this, it would not be a good assumption. I mean, realistically, they would put some sort of parachute, I would assume, on it to slow it down and have it land more gently on the ground. But we are ignoring air resistance nonetheless, which means the only acceleration that this package, I should say, is the acceleration due to gravity. So the acceleration is constant here, which means we can use the kinematic equations, the big three, as long as we use them separately for x and y. So horizontal motion and vertical motion are independent of each other. They are related through time, though. However much time it takes for the package to move this total distance horizontally is the time it's going to take for the package to drop the 100 meters. All right, so because acceleration is constant, we can use the kinematic equations. I recommend setting up the variables like we've been doing in previous problems that involved the kinematic equations. But again, because the motion is not a straight line, that's what we mean by two-dimensional motion. The motion, the trajectory of this package is not a straight line. That's how we know we need to break it into x and y components. So writing out our variables, and then that can help set up our equations. We do need to choose an origin. We can choose our origin wherever we want, really. We could either put it where the package is initially or at the ground, underneath where the package was released. The difference between that is just our initial and final positions. If I put my origin down here at the ground, then I'm saying the initial position for x is 0, but the initial position for y is positive 100 meters. Positive because this package is 100 meters above where I have chosen the origin to be. S final is this total distance, how far short of the target this package should be dropped. Y final is going to be 0 because the package is getting to the ground. V initial is the velocity of the plane because the package is originally in the plane. Again, I'm assuming the plane is flying parallel to the ground simply because it doesn't tell us some other angle that it was flying at. So that means the initial velocity of this package is completely in the x direction. There will be no velocity in the y direction initially. We do not know the final. Technically, we do know the x component is still going to be 150, but Vy final we don't know. That represents how fast this package of supplies is traveling downwards right before it hits the ground. The acceleration, we are assuming no air resistance, so no acceleration in the x direction. In the y direction, there is the acceleration of gravity downwards at 9.8 meters per second squared. And then time, we do not know the time. That's not been given to us. So ultimately, the question wants us to find x. How far short of the target should it drop the package? So final position, when I come over to my kinematic equations, the final position shows up in these two bottom equations. But in this third equation, when we're talking about the x direction, there is no acceleration in the x direction, which makes this whole third term cancel and disappear. So this third equation essentially tells us that the final velocity in the x direction will equal the initial velocity in the x direction. If a is 0, that whole third term is gone. And that happens with the top equation as well. So ultimately, in projectile motion, when we have an acceleration of 0, the middle equation, there's two ways we can write it. We can write it just with subscripts of x. Oops, not equals, sorry. There's no acceleration in the x direction. And so our equation for the horizontal portion of the motion simplifies to be the final x position, which I have just called x over in our table. In this case, because of our choice of origin, there's no initial x position. So this distance x that we're trying to find is going to depend on that initial x velocity, which we know, 150 meters per second, and then time, which we do not have. This is a nice, easy equation if we have the numbers to plug in. So in the x direction, this middle equation is the one that is helpful because the other two equations with that 0 acceleration shows us that the initial x velocity has to equal the final x velocity. So we get to this point and we need to know time. Well, the x information, I don't have enough information to find the time. So I need to come back and look at all this y information and see if I can get time from there. So we know the initial position, initial velocity, final velocity. We know everything in the y direction except for time and Vy final. Time is in the two top equations. The top one we would have two unknowns because we don't know Vy final. But let's look at the middle equation. So this middle equation, the final y position is going to equal the initial y position plus the initial y velocity times time plus 1/2 the y acceleration times time squared. Now you can write these s final y and s initial y if you want as well. That's a matter of choice. Specific to this problem, we know there's no final position because of how we chose our origin to be. We know there's no initial y velocity because the package of food is traveling horizontally initially. So right now, the equation has simplified. Let's go ahead and bring y initial over. I'm also going to multiply by the 2 and divide by a. This will equal t squared, which I then will take the square root of both sides. So negative 2, y initial was 100 meters. Acceleration in the y direction is downward, so negative 9.8 meters per second squared. Those negative signs will cancel, which is good. That's going to give us a positive number, which we need because we're not going to be using imaginary numbers. So plugging this in, just keeping a few digits out, and that's the wrong units. So our time, about 4.5 seconds. This tells me that it takes about 4.5 seconds for this package of food to drop 100 meters. But while it is dropping, it is also moving horizontally at 150 meters per second. So we can find how far it travels in that time. By plugging it back into this horizontal equation we were looking at before. Now, significant figures, this one's not particularly clear. The 100 is theoretically 1, and the 150 is 2 significant figures. So this would be approximately 700 meters in terms of going with the smallest number of significant figures. If these were exact, meaning the 100 was 3 significant figures and the 150 was 3 significant figures, then we would leave the answer as 678 meters. On an exam, as long as, if something ambiguous like this, I would accept 1, 2, or 3 significant figures. But as long as we're within one of what it should be, then I will give you full credit if it's the correct answer. So the setup, very similar to how we were approaching linear motion before, using the kinematic equations. The big difference here is needing to look at both x and y, writing out the information for x and y separately, and then using the kinematic equations using just the x information or just the y information.